All right, so now we are talking about vector functions, and this is really getting into calculus. We've been doing a lot of sort of algebra and coordinate geometry. Now we're ready to actually do some calculus. So as this is multivariate calculus, we're going to be either looking at functions which have more than one input or more than one output. And in this case, we're really looking at functions that have more than one output. So a vector valued function, or a vector function RT, is going to be a function which has domain in the real numbers, so it takes inputs that are real numbers, and range in some vector space, say 2 or 3 dimensional vectors. So generally we're going to assume that we're dealing with 3-dimensional vectors because that's where we are. That's what we've been dealing with a lot, but whatever. It could be 2-dimensional too, it could be 4-dimensional, it could be whatever. Anyways, the notation we're going to be using is this, and this is just our convention. If we look at R of t, it has components, and the components we're going to write down as f of t, g of t, and h of t. Now, f, g, and h are just regular old real valued functions. They're just functions that take one real input and spit out one real output. That's it. And so luckily we're going to be able to use that to analyze R of t, because we already have our constructions in calculus for functions of one input and one output. We can also write it as f of t I plus g of t j plus h of t k. Okay, so we can interpret R of t as being position vectors of points in space. And so we get a space curve, C. So here we have R of t being represented as a vector coming from the origin. As such, it is the position vector of the point f of t, g of t, h of t. As we let t vary, the point moves through space and we get some sort of curve. Now, if we just look at the individual coordinates, which are really the components of our vector function, we get parametric equations for C. X is equal to f of t, y is equal to g of t, z is equal to h of t. In this case, we then call t a parameter. To get any point on the curve, you just take some value of t that's in the domain of these guys, you plug it into each function, you get coordinates, you plot your point. Fantastic. Now, a really common situation that this occurs in is if we're considering C to be the trajectory of an object or a particle or whatever in space, and usually here t is going to be time. So this is sort of a nice scenario because then we can start talking about physics or things like that. And it's nice to interpret this as a vector function because then when we start doing things like taking derivatives, our derivatives are going to be vector functions themselves, and it makes more sense for us to think of, say, velocity as a vector than to think of velocity as being a point in space. Now, we've already seen some examples of vector functions, so if you need something to think about for the time being, think of these. We've already seen lines. These are already given to us as R of t is equal to some position vector r0, which represents a point on the line, plus v times t, where v is a vector that's parallel to our line. And component-wise, this is x0 plus at, y0 plus bt, and z0 plus ct. Those are our components. And we already saw that we can look at these individually as the parametric equations. Anyways, just a couple of notes. The domain of a vector function is the intersection of the domains of its component functions. So if we don't explicitly say where t comes from, we assume that t can be anything that can be plugged into f, g, and h. You might remember that we restricted the domain of t for a line to come up with line segments, rays, and other things. So unless we say otherwise, we assume that t can be whatever it can be. So for example, for a line, t can be anything unless we say otherwise. A vector function is continuous precisely when each of its component functions is continuous. And continuous here really means that as t moves along, there are no holes or gaps or jumps as you trace out the curve. And it turns out that if r of t is continuous, then the curve c has no jumps or holes or anything. The converse isn't true. You can have a curve which geometrically has no jumps or holes, but it does come from a non-continuous r, but whatever, we're never going to deal with that. So generally these two are the same thing, but just know that when we have nice looking functions, f, g, and h, then r is nice, and then our curve c is also going to be nice looking. All right, so let's do some actual calculus. We can define d dt of r of t, which is the same as r prime of t, and this is the derivative of r with respect to t, in an analogy to our usual definition of derivatives. So I'm going to write this down once and then never talk about it again. R prime of t is the limit as h goes to 0 of r of t plus h minus r of t divided by h. So really what this is we're taking the correct way of interpreting this is a displacement vector between 2 points on our space curve, and we're dividing by an interval of the parameter. So it's really looking at the rate of change along our space curve with respect to the parameter, and if we let the parameter go to 0, we should get the instantaneous rate of change along our space curve, or the instantaneous rate of change of our vector value function with respect to the parameter. So here's the fact. The derivative of our vector function is equal to the vector of the derivatives of our component functions. So to differentiate r, I just differentiate f, g, and h. Now, a really good interpretation of this is to let t represent time, and so r of t is the position of some object in space, then r prime of t is the velocity vector. Each component tells you how fast the object is going in each direction at time t. So this is nice. Now we can actually talk about motion in three-dimensional space instead of just what you're sort of stuck with in Calc 1 and Calc 2, motion in one dimension. Okay, so we have some good interpretations of this vector, or some good constructions with this vector r prime of t when it's not equal to 0. First of all, r prime of t when it's not equal to 0 is the tangent vector to the space curve at the point f of t, g of t, h of t. This means that it is, you know, pretty much going in the same direction as the curve is at that point. Fantastic. Second, the tangent line, which is the best linear approximation to the space curve at a point when t is t0, some fixed time t0, or some fixed parameter, is, I'm just calling it L sub t0, just to give it a name, the tangent line. But it's given by r of t0 plus r prime of t0 times t. So this derivative is really analogous. This vector, which is the derivative of our vector function, is really analogous to the slope of a tangent line. But it's not quite a slope, it's a direction and a magnitude. It's actually giving us a little bit more information than a slope normally does. So great, this is very similar to what we did in Calculus 1. Also, we have something called the unit tangent vector, because there is not a unique vector that is parallel to a line, or there's not a unique vector that is tangent at a curve. So oftentimes, if we're just concerned with the geometry of a curve and not really the idea of an object moving along the curve over the course of some period of time, a canonical vector to look at is something called the unit tangent vector. We take our vector and we divide by its magnitude. So it gives us a unit vector which is tangent to our curve at a point. R prime of t gives us a little more information if we interpret our parameter t as time, and then we're looking at, r prime is the velocity vector or whatever. But if we're just looking at the geometry of c, this is a more natural sort of tangent to look at.